Today, we will basically discuss one important inequality that is again due to Kolmogorov, which is known as Kolmogorov's maximal inequality, or in short Kolmogorov's inequality. The importance can be seen in many ways, as for example, this actually involves or provides the upper bound and also a lower bound to a particular kind of event, which is maximum of modulus of partial sums, which is greater than equals to epsilon. So, probability of this event, it can be, it is very difficult to calculate this event, probability of this event, but all we can do is that we can provide at least an upper bound and lower bound to this probability. So, this inequality should not be looked just as giving some bounds to a particular probability event, but this is very important in proving several other results in probability theory, because it has a huge impact in proving some convergence theorems in probability. Also, another important thing is that these inequalities are very nice in the sense that this involves only very weak conditions, as for example, just the existence of second order moments. So, along with that, we can with the assumption of this second order moment, we can provide a bound, especially the upper bound and also the lower bound, but sometimes we have to impose some other extra conditions in order to get the proper bounds. So, today we will discuss only this inequality in great detail, its statement and under what conditions we can provide these bounds and the detailed proof of this inequality. So, now we will state and also prove Kolmogorov's maximal inequality. Now, Kolmogorov's maximal inequality, or simply Kolmogorov's inequality, is actually an extremely important tool in probability theory. It actually gives us two bounds, one upper bound and another lower bound to a probability of a particular event that is relating to sum of random variables and so on. We will see immediately. Another important fact that I should mention, that this inequality is plays a central role in proving strong law of large numbers. So, we will see later that Kolmogorov also developed some strong laws of large numbers, and using this Kolmogorov's maximal inequality, that strong law, or SLN, strong law of large number, can be proved. So, this actually is a very important tool and result in probability theory and is used in many situations. So, now let us state this Kolmogorov's maximal inequality. Note that here we consider a sequence of independent random variables. So, the condition of independence is very important in this case. So, suppose x1, x2, xn and so on be independent random variables, and expectation of xn square is less than infinity. That means, here also we assume the existence of second order moment and no higher order moment. At this moment we are not assuming the existence of any higher order moment. So, moments up to second order is enough to prove this Kolmogorov's inequality. Now, expectation of xn square less than infinity for n greater than equals to 1, that means for every n. Define Sn, that as usual, that is summation of xi I equals to 1 to n and epsilon greater than 0, that means you choose epsilon greater than 0. Then probability maximum over 1 less than equals to k less than equals to n modulus of sk minus expectation of sk greater than equals to epsilon. This probability is bounded above, that means less than equals to summation sigma k square k equals to 1 to n divided by epsilon square. So, this first part of this inequality gives us the upper bound only under a very mild condition of the existence of second order moment. Now, Kolmogorov also developed another result relating to the lower bound. That means, this same probability of the same event is greater than equals to something, provided another condition is needed. That is, if moreover we assume that mod of xk less than equals to c, where c is less than infinity almost surely, then probability of maximum of 1 less than equals to k less than equals to n modulus of sk minus expectation of sk greater than equals to epsilon is greater than equals to 1 minus epsilon plus 2c whole square divided by sigma k square k equals to 1 to n. That means, here along with the assumption of existence of moments, we also assume that mod xk is less than equals to is bounded by the constant c, which is finite, and under this condition we can give a lower bound to this same probability. Let us now prove this Kolmogorov's inequality. First we will prove the upper bound and then we will prove the lower bound. To prove the upper bound, first assume without loss of generality that expectation of xk equals to 0 for k greater than equals to 1. Now, define a random variable. We call this random variable, we can give a name to this random variable which is stopping time, random variable t, by defined by t equals to first k, where k lies between 1 and n, such that sk square greater than equals to epsilon square, if there is such a k. That means, if we can find a k such that sk square, sk is summation xk, k equals to 1 to n say. So, sk square greater than equals to epsilon square, otherwise if we do not find such a k, otherwise it will be n plus 1. Then it is clear that maximum of k less than equals to n modulus of sk greater than equals to epsilon is exactly same as the event t less than equals to n, because here this is the first time sk square greater than equals to epsilon square, which means that modulus of sk greater than equals to epsilon. If such a k holds, then t must be less than equals to, then k must lie between 1 and n. So, t must be less than equals to n. Let us call this as equation 1, and it is pretty obvious that t equals to k, the event t equals to k belongs to the Borel sigma field generated by x1, x2, xn. We have already defined what is the meaning of Borel sigma field generated by a sequence of or a set of random variables. So, it is immediately obvious that t equals to k belongs to such a sigma field generated by x1, x2, xn. Now, one important point that I already mentioned probably, that this inequality is very important, no doubt about that, but we should also look into the technique how it is proved. This is a very nice technique and it can be applied anywhere in mathematics or in probability or in statistics. So, let us consider first this quantity, that is integration over t equals to k sk into Sn minus sk dp. Now, p is the probability measure on which probability measure defined on the space. Now, this is a product term, sk into Sn minus k is a product term. We will see what is the implication of this product term, or what is the implication of considering this term at this moment. So, let us first calculate this thing or explore its property. So, integration t over t equals to k over the set t equals to k sk into Sn minus sk dp equals to, we can immediately write expectation of sk into indicator function, indicator over the event over the set t equals to k into Sn minus sk. Now, note that Sn minus sk actually belongs to the sigma field generated by xk plus 1 to xn, and sk or t equals to k, this event belongs to the sigma field generated by x1, x2, xk. Now, x1, x2, xn, they are all independent random variables. So, this part sk into I of t equals to k and Sn minus sk, they are actually basically independent. So, immediately we can write expectation of sk into I t equals to k into expectation of Sn minus sk. Now, since expectation of xi equals to 0 for every I, we immediately see that expectation of Sn minus sk, which is equals to expectation of xi, I equals to k plus 1 to n, which is equals to again 0. So, this quantity integration over the set t equals to k sk into Sn minus sk dp is exactly equals to 0. Now, here we have used the condition of independence. So, we have to note that this is one step where we use the property of the independent random variables. Now consider integration t equals to k Sn square dp, which is equals to, we can write Sn as Sk plus Sn minus Sk. So, this is exactly equals to integration over t equals to k Sk plus Sn minus Sk whole square into dp. Just simplify using that a plus b whole square formula, we immediately get integration over t equals to k Sk square plus Sn minus Sk whole square plus 2 into Sn minus Sk into Sk dp. Now, if we recall the result, just what we have proved just now, that is integration over this product term equals to 0. So, we immediately have this entire quantity is greater than equals to integration of Sk square dp over t equals to k, because we dropped the second term, which is greater than equals to epsilon square, because the entire thing actually is working on the set on the condition that Sk square greater than equals to epsilon square. So, if we replace Sk square by epsilon square, there will be a greater than equals to sign. So, it would be epsilon square into probability of t equals to k. So, what we get, integration over t equals to k, the set t equals to k, Sn square dp is greater than equals to epsilon square into probability t equals to k. Let us call this inequation as 2. Now, what is expectation of Sn square? Expectation of Sk equals to 0. So, expectation of Sn square is nothing but expectation of Sk square, k equals to 1 to n, and the product term will vanish because x1, x2, xn are independent. And so, naturally this equals to exactly equals to summation sigma k square, k equals to 1 to n. Now, this is true for every k, these conditions that x1, x2, xn are independent, and expectation of xk equals to 0, or this actually holds for every k greater than equals to 1. So, now from equation 1 and if we use equation 2, in equation 1 we immediately get probability maximum over 1 less than equals to k less than equals to n modulus of sk greater than equals to epsilon, which is equals to probability t less than equals to n, because we have already seen in equation 1 these two events are exactly same. Now, this probability t less than equals to n we can immediately write as summation k equals to 1 to n probability t equals to k, and we have just seen in equation 2 this is less than equals to 1 by epsilon square summation k equals to 1 to n integration over t equals to k Sn square. That is, actually we have seen that probability t equals to k is less than equals to 1 by epsilon square into integration over t equals to k Sn square dp. Now, this is again equals to 1 by epsilon square integration over t less than equals to n, because t equals to k and there is a summation outside. So, combining this we can write integration over t less than equals to n Sn square dp. Now, if we just remove this restriction and make it the whole, consider the integral over the whole space. So, this will be again less than equals to 1 by epsilon square integration over of Sn square dp, which is nothing but expectation of Sn square. And we have seen that expectation of Sn square is summation sigma k square, k equals to 1 to n. So, ultimately what we get in the right hand side as 1 by epsilon square into summation k equals to 1 to n sigma k square. So, this basically gives us the upper bound to this probability. Now, let us prove the part B, which is the lower bound. This is little bit more technical, but just some manipulation and simplification, nothing more than that. It looks like complicated, but it is not really very complicated. So, first consider f k as indicator function of t greater than equals to k, greater than k, not equals to t greater than k. Therefore, f k, sk and x k plus 1 are independent for k equals to 0, 1 up to n minus 1. And also note that t greater than k is nothing but t less than equals to k complement. Now, t less than equals to k belongs to the Borel sigma field generated by x1, x2, xk. So, its complement will also belong to the same sigma field, and hence we can immediately say that t greater than k, this event also belongs to the Borel sigma field generated by x1, x2, xk. Now, note one thing, that if we consider expectation of fk into sk into xk plus 1, and we have seen that fk sk is independent of xk plus 1. So, we immediately have expectation of fk sk into expectation of xk plus 1, which is equals to 0. Hence, after a little bit of simplification, if we write expectation of sk square fk minus 1, we can write, you see, fk minus 1 is nothing but an indicator function. So, we can immediately write expectation of sk square into fk minus 1 square, and we can also write sk as sk minus 1 plus xk. So, putting that thing here, we have expectation of sk minus 1 fk minus 1 plus xk fk minus 1 whole square, and just considering that old formula a plus b whole square, and after a little bit of simplification, product term will vanish naturally. We immediately have expectation of sk minus 1 square into fk minus 1 plus expectation of xk square into probability t greater than k minus 1. Now, again, since f of k minus 1 we can write as f of k plus I of tk minus 1, we have immediately that expectation of sk square fk minus 1 equals to expectation of sk square fk plus expectation of sk square I t equals to k, and hence from the previous equation we have expectation of sk minus 1 square into fk minus 1 plus expectation of xk square into probability t greater than k minus 1 is nothing but expectation of sk square, the left side in the above equation, expectation of sk square fk minus 1 equals to expectation of sk square fk plus expectation of sk square into I t equals to k. Now, we apply the additional condition, that is the boundedness condition, that is, since modulus of xk less than equals to c for every k, we immediately have modulus of xk minus expectation of xk is less than equals to 2c. So, from here, putting this condition and after a little bit of simplification, we can write expectation of sk minus 1 square fk minus 1 plus, that means the right hand side in the above equation, plus expectation of sk square into probability t greater than equals to k is less than equals to expectation of sk square fk plus, we put this condition, that is epsilon plus 2c whole square into probability t equals to k. Now, again we apply the same condition and take the sum in the previous equation for k equals to 1 to n. We will see that many terms will cancel each other, then finally we get expectation summation expectation of xk square into probability t greater than equals to k, which is less than equals to expectation of sn square into fn plus epsilon plus 2c whole square into probability t less than equals to n. Now, by the definition of t, if you recall the definition of t, this gives us sn square fn square is less than equals to epsilon square, and so probability t greater than n is less than equals to probability t less than equals to n if k is less than equals to n. Hence, expectation summation k equals to 1 to n expectation of xk square into probability t greater than n is less than equals to epsilon square into expectation of fn plus epsilon plus 2c whole square into probability t less than equals to n. And immediately we see, after application of all such inequalities, immediately we see that this is the n less than equals to epsilon plus 2c whole square into probability of t less than equals to n plus epsilon plus 2c whole square into probability t greater than n, which is nothing but adding these two we get simply epsilon plus 2c whole square. So, all we get is probability t less than equals to n is equals to 1 minus probability t greater than n, which is actually this probability t greater than is nothing but the old event for which we are going to calculate this bound, that is maximum with respect to modulus of sk, and this probability is greater than equals to 1 minus epsilon plus 2c whole square divided by summation sigma k square k equals to 1 to n. So, here this gives us the lower bound of Kolmogorov's lower bound to this probability of maximum of modulus of sk, because we have assumed with the loss of generality expectation of sk to be 0. So, now Kolmogorov's inequality gives us two things, one is an upper bound, another is a lower bound, but remember one thing, that lower bound is calculated under a special assumption which is modulus of xk less than c, where c is finite. So, we have discussed the detailed proof of an extremely important result due to Kolmogorov, known as Kolmogorov's inequality or Kolmogorov's maximal inequality. We have seen that we have proved this inequality only under the assumption of existence of second order moment, and for one particular bound, the lower bound, we have assumed some boundedness condition. Now, all these conditions are very natural in practice, so it is not really an worrying factor, or it is very easy to check these conditions, and in most of the situations these conditions hold. But another important point which I want to emphasize, that if you look at the technique of the proof, you will see some interesting techniques or tools that has been used. Sometimes we start with a particular quantity and later we see that the proof follows immediately from if we just study that particular quantity. So, in probability or in any area of statistics also, it is important to visualize whether we can work with a quantity which will immediately give us or lead us to the proof. So, so along with the understanding of this inequality and its proof and the importance of this result, we should also try to keep in mind the technique and the tools that has been used. So, the idea is that sometimes we have to visualize some quantity, sometimes we have to introduce some new variables so that the proof would be extremely easy. So, that should be the take home message for the entire proof or entire discussion that we need today.